We don't often get a chance to look at other systems that we don't actually use in the lab at school. But this method is actually one of the ones that's going to be tested in your exam, so we need to have a bit of a closer look at it. So let's have a look at hydrogen NMR spectra. I've already gone through spectra with you. Now, what we do is we use nuclear magnetic resonancing and to look at the structure. Now, this helps us work out the structure of very, very complex molecules. Now, in some cases, they not only look at the way hydrogen behaves, but also how carbon or someone else or some other element behaves. And in both cases, we actually use long wavelength radio waves to align atoms inside a magnetic field. And this produces a pattern or a spectra that we can actually then analyse. As we know, with any sort of a referencing system or any sort of a thing, we have to calibrate it. Now, the calibrating system is using a thing called TMS. Proper name, tetramethylsilane. It's actually a silicon molecule or a silicon atom which has 4 methyl groups attached. All right? Now, the reason we can use this one is because every one of the hydrogens in that the methyl groups all have the same neighbourhood, so we say they are all in the same environment. And this ensures that they only provide us with a single peak. What actually goes on? You've heard me talk about environments, and that is basically looking at what your neighbours, their effect on you, right? Hydrogen, we know, can exist in various forms and can exist in various patterns, if you like, in a typical organic compound. So we can have things like CH3 groups, right, or CH2 groups, or even hydroxy groups, or we go to amine groups and goodness knows what. So we can sort these out because they have different surroundings, if you like, and different neighbours. Now, the number of hydrogens in each of these will influence the peak size. So in general terms, we could say the higher the peak, the more hydrogens are involved in making that peak. Neighbouring molecules, though, also have an effect on the peak, but instead of making it higher or lower, they shift it, and this is referred to as chemical shift. Now, if you go and have a look in your data book, and I think it's around about table number 26 or 27, you will find the chemical shifts associated with certain patterns. In other words, we look at what is attached to the carbon which has got the hydrogens on it that we're interested in. This sample actually goes into too much detail. This is more a high level NMR, and we actually have peak splitting. Now, peak splitting is covered in the high level course, but we don't have to do it. But from this, we can obviously see that there are 3 different ways that hydrogen exists in this molecule. In other words, there are 3 different hydrogen environments. And the number of peak splits is to do with the neighbours. Now, I would suggest to you that the one around about 1 ppm is probably going to be a CH3 or a CH2 group. And if you look back at the chemical shift information, you'll see that is where they seem to be concentrated. Now, luckily, we're very, very much helped in all this. Sometimes we can actually see what's called an integration marker. Now, the integration marker helps us compare the heights of the peaks, and essentially that tells us the ratio of hydrogens causing the peaks and allows us to compare them. The peak splitting I talked about before, as it says here, confirms the number of hydrogens in each environment, but for the purposes of the standard level, we do not have to worry about that. Now, so what's this all about? Well, magnetic resonance imaging is used in human body scans, which is really, really handy, because if we want to know how your body is actually working, we can actually cause the hydrogen in water molecules to move around a little bit, and we can actually produce real-time pictures of what's going on in your body. And the big thing about it is it's non-destructive. A lot of the techniques we use in chemistry to actually analyse the sample, especially instrumental analysis, we actually destroy the sample. But we obviously don't want that. If you're going into hospital to have a MRI, magnetic resonance imaging, then we don't really want to lose part of our body or have it destroyed as we're having it tested. So it's very, very handy for us to have to do this. And as it says here, we work very, very much due to the high water content in your body, and it makes it exceptionally good for soft tissue examination. In other words, organs and tissues that we don't really see if we do x-rays. But it also offers real time. You actually see them working and see them in operation if you are carefully done.